Okay, so we're going to talk very quickly about TCP/IP and a little bit about Ethernet, mostly TCP/IP. Of course, TCP/IP, as you well know, is the Transmission Control Protocol Internet Protocol. The name, of course, is really the name not of two protocols, but of an entire protocol stack. TCP, layer 4, IP at layer 3, and there's a whole bunch of other stuff that goes on with it. Interfacing down with Ethernet at layer 2, going all the way up to the application layer and the fun things we play with, like web services and HTTP and files and email and management and paying and yada yada yada. This was originally developed in the 1960s. It is a whole protocol suite, a protocol stack, defining how to format, segment, desegment, encapsulate, de-encapsulate the data in question at various layers of the model. It uses its own address scheme, which we are familiar with very familiar with right now, which is separate from layer 2 addressing, MAC addressing. Technically speaking, TCP/IP doesn't have to run on top of Ethernet. It could just as easily run on top of, say, frame relay, or point-to-point protocol, or asynchronous transfer mode, or whatnot. There are two versions in use today, IPv4, which dates from the 1960s, and IPv6, which dates from the 1990s. IPv6 has a much larger address space, as you well know, and therefore a different address structure. IPv4 uses 32-bit addresses, dotted decimal. Each address contains a network ID and a host ID, and we figure out which is which using the subnet mask, which is a string of ones followed by a string of zeros. TCP/IP also includes v4 specifically, private IP addresses reserved for private internal networks not routable across the internet. This concept also shows up in IPv6, where it's called a link local or a site local address. If you see an address that looks like FE80:: something, that's a link local. I think FF02, that range is multicast, tends to function link local, or at best site local. The class A address, there's a loopback address in v4, which is the 172.0.0.0/8 range. So technically, all loopbacks, everything between 192.0.0.1 and 192.255.255.254 is available for loopbacks. Say, for example, if you implement Net Time Protocol, the NTP, on a Cisco router, and you tell the Cisco router in question, you're the NTP master, what it will do is decide that it'll make up a loopback for itself, 127.127.something.something. And the process, the physical NICs, the physical interfaces which you configure on that Cisco router will refer to that loopback, and it will be the NTP master. Everything else will talk to those downstreams. Anyway, so one of the ways we have to give these out is DHCP, the Dynamic Host Configuration Protocol. You'll have a computer or potentially a cluster of them running on the network to provide DHCP. This can be a router, or a broadband router, a Cisco ISR, a Linux box, a Windows box, a domain controller, a standalone machine. This allows us to provide IP addresses, masks, gateways, domain names, DNS addresses, WINS addresses, the whole 9 yards. And your clients will reach out to that, asking for an IP address. If they get it, great. If they don't, the computer will actually use automatic private IP addressing, a PIPA. That will always look like 169.254.0.0 or /16. So that range that you see in front of you. If you see one of those and you don't intend to see that, you have a DHCP failure somewhere along the line. It could be the DHCP server is down. It could be you have a layer 1 issue, or a layer 2 issue, or a layer 3 issue. If you haven't already studied this, how to troubleshoot DHCP, hopefully you will get that in your routers course. But I don't have time to get into that now. So, graphically presenting this would, if you, this image here, say 172.16.122.204, this is with a /16 subnet mask. That's 255.255.0.0. You can tell that it's a /16 because your 32-bit address space is evenly divided. If 172.16.122, if that were the network address and 204 were the host address, that would be a /24, and it can get more complicated than that. The subnetting is another one of those things you really need to understand. So if you are still working on it, keep working on it. If you are working on it and it's confusing to you, by all means say something. Tell your instructor, reach out, help us help you. Because this is another one of those things you need to understand cold. And then our private address ranges. Every class A, Class B, and Class C in IPv4 have private ranges. These are really good for things like virtual networking and private address spaces that you don't really need to route across the internet. Say if you virtualize a SAN inside your ESXi cluster, there's really no reason whatsoever, because that SAN only exists to talk to those vCenter servers, or rather its client machines, that they should never see the outside world. So private addressing is perfectly all right for them. One note, there is no private address range for Class D, which is multi-classed, and no private range for Class E, which is experimental. If we're doing this with IPv6, we could do that with either link local or site local. So that is TCPIP in a very, very small nutshell. There's so much more to it than this. So if there are parts of this are a little bit confusing to you, go back and review your some of your other textbooks from other courses, because you're likely to find this kind of information repeated over and over and over again. Thanks, and then now we'll start talking about virtual switches.